What is nothing? It's a question that seems simple but has puzzled thinkers for centuries. Is it a void, an empty space, or something more mysterious? Philosophers have debated its meaning. Scientists have studied its properties, and artists have tried to capture its essence. Join us as we explore the concept of nothing. The universe is a grand stage of existence, an expanse that encompasses all of space and time, the very fabric in which galaxies, stars, and planets find themselves situated. Estimations suggest that the observable universe stretches over 93 billion light-years in diameter. Perhaps even more mind-boggling than its size is its age, around 13.8 billion years. This immense realm contains an approximated 2 trillion galaxies, each harboring millions or even billions of stars. But the universe isn't just a collection of celestial bodies. It's a symphony of particles and forces, a constantly evolving entity governed by the laws of physics. Scientific theories like the Big Bang model offer insights into the universe's origins, positing that it began as a singularity, an infinitely dense point, and has been expanding ever since. Dark matter and dark energy, though not directly observable, are believed to make up about 85% of the universe's mass and influence its expansion and structure. As we gaze into the cosmos with ever more sophisticated telescopes and instruments, we continue to unravel the astonishing complexities hidden within this boundless expanse, deepening our understanding of what the universe truly is. The vastness of the universe defies comprehension, stretching the limits of our imagination and understanding. To paint a picture, the observable universe extends 93 billion light-years in diameter. In other words, light, which travels at an astounding speed of about 186,000 miles per second, would still take 93 billion years to traverse the observable cosmos from one end to the other. This enormous expanse hosts an estimated number of galaxies that stands at 2 trillion, each galaxy housing billions of stars and potentially even more planets. Our own Milky Way galaxy, a relatively standard spiral galaxy, contains about 100 billion stars. Yet, the limit of the observable universe does not imply a boundary. Rather, it's the furthest distance from which light has had time to reach us since the Big Bang. Beyond this observable limit, there may be much more of the universe that remains unseen and, perhaps, for now, unknowable. This immense scale challenges not just our scientific instruments, but also our philosophical perceptions of our place in the cosmos. It makes the realization sink in that, within this mind-boggling immensity, our Earth is but a mere speck, a tiny fragment drifting through a timeless and boundless ocean of space. The observable universe refers to the portion of the entire universe that we can see and study with the aid of our current technology and scientific methods. It's a concept bounded not by physical walls, but by the limits imposed by the speed of light and the age of the universe. Given that the universe is about 13.8 billion years old, the furthest distance light has traveled to reach us is also approximately 13.8 billion years. However, due to the ongoing expansion of the universe, the actual distance to the edge of the observable universe is around 46 billion light-years in every direction, cumulatively resulting in a diameter of about 93 billion light-years. This observable cosmos contains an immense variety of astronomical phenomena, from sparkling galaxies and star clusters to enigmatic black holes and glimmering nebulae. Despite the observable universe's overwhelming expanse, it might represent only a fraction of the total universe, which some cosmological models suggest is far larger, possibly even infinite. Scientists use tools like a Hubble Space Telescope and the recently launched James Webb Space Telescope to probe as deeply as possible into this vastness, capturing light that has traveled for billions of years to give us glimpses of distant corners of the cosmos. While limited by the speed of light and the universe's age, the observable universe offers a profound window into the history, structure, and evolution of the cosmos. Measuring the size of the universe is an endeavor that combines cutting-edge technology with sophisticated scientific theories. At the heart of this measurement is the speed of light, which acts as a cosmic ruler. Light travels at approximately 186,000 miles per second, and by observing light from distant celestial objects, we can measure how far it has traveled over billions of years. This forms the basis for determining distances within the observable universe. One of the principal tools used by scientists is redshift, the phenomenon where the light from distant galaxies shifts toward the red end of the spectrum due to the expansion of the universe. The further away a galaxy is, the more its light is redshifted. This relationship, known as Hubble's law, allows scientists to calculate the distance to far-off galaxies. Coupled with advanced instruments like the Hubble Space Telescope and the newer James Webb Space Telescope, astronomers can measure these distances with unprecedented accuracy. Additionally, other methods, such as observing Type Ia supernovae, stellar explosions with a known intrinsic brightness, serve as standard candles to measure astronomical distances. Cosmic microwave background radiation, the afterglow of the Big Bang, provides a snapshot of the early universe and helps refine estimates of its size and age. Through these approaches, scientists have deduced that the observable universe spans about 93 billion light-years in diameter. However, the ultimate size of the entire universe beyond the observable part remains an intriguing and open question, potentially extending infinitely or existing as part of a larger multiverse. The universe is a grand tapestry woven with a myriad of components, each contributing to its intricate structure and dynamic nature. At the broadest level, the universe is composed of massive galaxies, vast assemblies of stars, planets, gas, dust, and dark matter, all bound together by gravity. There are an estimated 2 trillion galaxies in the observable universe, ranging from tiny dwarf galaxies to colossal giants. Our own Milky Way is a spiral galaxy, home to around 100 billion stars. Stars are the luminous engines of the cosmos, undergoing nuclear fusion to produce light and heat. These stars can vary immensely, from smaller red dwarfs to massive blue giants and supergiants. Some stars end their lives in spectacular explosions called supernovae, giving birth to neutron stars or black holes. The remnants of these explosions enrich the surrounding space with heavier elements, facilitating the formation of new stars and planetary systems. Planets, often orbiting around stars, come in diverse forms and sizes, from rocky terrestrial planets like Earth and Mars to gas giants like Jupiter and Saturn. Some systems even have exoplanets, planets orbiting stars beyond our solar system. Additionally, smaller celestial objects like moons, asteroids, and comets add to the complexity of stellar systems. Interspersed within and between galaxies is interstellar and intergalactic space, teeming with gas and dust, the raw materials for star formation. Dark matter, although invisible and only detectable through its gravitational effects, account for roughly 85% of the universe's mass. Even more mysterious is dark energy, a force thought to drive the accelerated expansion of the universe, making up about 68% of its total energy content. Together, these components create a universe of extraordinary diversity and complexity, offering endless avenues for exploration and discovery. Defining nothing in the context of the universe's origin is a concept that stretches the boundaries of both scientific understanding and philosophical contemplation. In everyday language, nothing might imply a complete absence of everything: matter, energy, even space and time. However, when it comes to cosmology, the notion of nothing becomes more nuanced and complex. Before the Big Bang, which marks the beginning of our universe approximately 13.8 billion years ago, there wasn't just an empty void. Even the fabric of space and time itself did not exist. One way scientists attempt to conceptualize this nothing is through the lens of quantum mechanics and the vacuum state. In quantum theory, even a perfect vacuum isn't truly empty. It's seized with temporary particle-antiparticle pairs that pop in and out of existence, a phenomenon known as quantum fluctuations. Thus, while nothing in the cosmological sense isn't simply an empty void, it signifies a profound absence of the structures and forces that came into being with the birth of the universe. The universe's inception provokes existential reflections, tapping into our innate desire to comprehend our place in the grand scheme of things. Scientific theories about the universe's origin, from the Big Bang to cosmic inflation, challenge and expand our worldviews, prompting us to rethink concepts of time, space, and existence. This inquiry also fuels technological advancements and scientific breakthroughs. The quest to understand the early universe drives innovations in fields ranging from astronomy to particle physics, leading to the development of cutting-edge telescopes and particle accelerators. Thus, seeking answers to the universe's origin is not only about tracing the cosmic timeline, but also about pushing the boundaries of human knowledge and inspiration. Ancient civilizations, long before the advent of modern science, crafted intricate and imaginative narratives to explain the origin of the universe. These creation myths not only provided a framework for understanding the cosmos, but also imbued it with cultural, spiritual, and moral significance. In ancient Mesopotamia, for instance, the Babylonian creation epic, The Enuma Elish tells the story of how the god Marduk defeated the primordial sea goddess Tiamat and used her body to create the heavens and the earth. This myth intertwined the origins of the cosmos with themes of order triumphing over chaos. In ancient Egypt, creation myths often centered on the god Atum, who emerged from the chaotic waters of Nun to form the world. Atum was believed to have created himself and then produced the gods Shu and Tefnut, who in turn gave birth to Geb, earth, and Nut, sky, establishing the basic components of the universe. These stories provided ancient Egyptians with a sense of continuity and divine order in their environment. The ancient Greeks offered a variety of narratives, with Hesiod's theogony being one of the most influential. According to Hesiod, the universe began with chaos, a void or nothingness, from which emerged Gaia, earth, Tartarus, the underworld, and Eros, desire. These primordial entities gave rise to the gods and the physical world. The Greek myths often emphasized the gods' roles in shaping the universe and human destiny, reflecting the Greeks' views on power, morality, and the natural order. Similarly, in Hindu cosmology, the Rig Veda describes a universe that emerged from a cosmic egg, Hiranyagarbha, and underwent cycles of creation, preservation, and destruction involving gods like Brahma, Vishnu, and Shiva. These cycles, known as yugas, illustrate a universe in constant flux, governed by divine will and cosmic laws. These ancient explanations were deeply embedded in the cultures and religious practices of their respective societies. They provided not only cosmological insights, but also ethical guidelines, social structures, and a sense of identity and purpose for people. While these myths differ widely in their specifics, they share a common goal: to elucidate the mysteries of the universe and humanity's place within it, weaving together the known and the unknown into narratives that could be passed down through generations. The creation of the universe has been the subject of countless mythological stories across different cultures, each imbued with its own unique symbolism, deities, and cosmic events. These stories serve as windows into the worldviews and values of the civilizations from which they originated. In Norse mythology, the creation of the universe involved a dramatic clash between primordial forces. According to the Prose Edda, the cosmos began with a yawning void called Ginnungagap, flanked by Niflheim, a realm of ice and mist, and Muspelheim, a land of fire. When the ice and fire met in Ginnungagap, they created Ymir, a giant, and Ordhumbla, a great cow whose milk nourished Ymir. From Ymir's body, the gods Odin, Vili, and Ve fashioned the world. His flesh became the earth, his blood the oceans, and his bones the mountains. The sky was formed from his skull, and his eyebrows created Midgard, the domain of humans. In Chinese mythology, one of the most famous creation stories is that of Pangu. According to this myth, the universe was originally an egg containing chaos and the opposing forces of yin and yang. Pangu, a giant, emerged from the egg, separating yin from yang with his strength. As he grew, he pushed the sky upward and the earth downward, creating the world. Upon his death, his body transformed into various elements of the natural world. His breath became the wind, his voice thunder, his eyes the sun and moon, his body the mountains, and his blood the rivers. The Maori of New Zealand have their own account of the creation, called the separation of Rangi and Papa. In this myth, the Sky Father, Rangi, and the Earth Mother, Papa, were locked in a tight embrace, leaving their children, the gods, confined in darkness. The gods conspired to separate their parents to bring light to the world. After many attempts, the god Tani Mahuta succeeded in prying them apart, with Rangi becoming the sky above and Papa the earth below, thus creating the world and making space for all living things. These stories, while diverse in their details and characters, often share common themes: the struggle between order and chaos, the transformation of primordial entities into the physical world, and the involvement of divine beings in shaping the cosmos. They illustrate how ancient cultures sought to make sense of the existence and structure of the universe, grounding their understanding of reality in rich narrative traditions that have been passed down through generations. Early philosophers and scientists laid the groundwork for our contemporary understanding of the universe by transitioning from mythological explanations to more rational and observational approaches. Their views on the universe were deeply influenced by their observations, philosophical frameworks, and the limitations of their times. In ancient Greece, thinkers like Thales of Miletus began to speculate about the natural world using reason rather than mythology. Thales proposed that water was a fundamental substance of the universe, thinking that all matter originated from it. Anaximander, a pupil of Thales, suggested a more abstract concept called the apeiron, an infinite and indefinite substance from which all things emerge and return. Heraclitus of Ephesus introduced the idea of change being central to the universe, encapsulated in his famous phrase, "You cannot step into the same river twice." Plato and his student Aristotle offered more complex philosophies regarding the universe's nature. Plato conceived of a cosmos fashioned by divine craftsmen, the demiurge, who imposed order on chaotic pre-existing matter. His work, Timaeus, laid out a universe where the earth was at the center, surrounded by perfect circular motions of celestial bodies, reflecting his belief in a harmonious and ordered cosmos. Aristotle further elaborated on this geocentric model in his work, On the Heavens. He argued that the universe was finite and spherical, with Earth at its center and surrounded by concentric celestial spheres. To Aristotle, the heavens were unchanging and made up of an ethereal substance called ether, distinct from the corruptible materials found on Earth. The Renaissance and the subsequent scientific revolution ushered in transformative views of the universe, significantly departing from earlier geocentric models. Nicolaus Copernicus proposed a heliocentric model, placing the sun rather than the earth at the center of the universe. This revolutionary idea, later supported and refined by astronomers like Galileo Galilei and Johannes Kepler, laid the groundwork for Isaac Newton's laws of motion and universal gravitation, providing a mechanistic understanding of how celestial bodies interacted. These paradigm shifts not only redefined our conception of the universe, but also marked the evolution of science from philosophical speculation to empirical inquiry. Thus, early philosophers and scientists viewed the universe through a complex interplay of observation, speculation, and evolving methodologies, setting the stage for profound advancements that came with the modern scientific era. The Big Bang Theory is a leading scientific explanation for the origin and evolution of the universe. It posits that, approximately 13.8 billion years ago, the universe began as a singularity, an infinitely dense and hot point where all matter, energy, space, and time were concentrated. This singularity then underwent a massive and rapid expansion, a process not to be confused with an explosion in the conventional sense, which marked the beginning of the universe as we know it. As the universe expanded, it began to cool, allowing the formation of subatomic particles and simple elements. Within the first few minutes of this rapid expansion, known as the period of nucleosynthesis, protons and neutrons combined to form the nuclei of hydrogen, helium, and small amounts of lithium. The universe was still incredibly hot and dense during this time, with light unable to travel freely due to constant interactions with particles. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with these nuclei, forming neutral atoms in a process called recombination. This event allowed photons to travel through space, leading to the decoupling of matter and radiation. The released photons are detectable today as a cosmic microwave background, CMB, radiation, a faint but pervasive glow that fills the universe and serves as one of the strongest pieces of evidence for the Big Bang Theory. Over billions of years, the gravitational attraction between particles led to the formation of stars and galaxies. These early galaxies began to cluster into larger structures under the influence of dark matter, a mysterious and invisible form of matter that interacts gravitationally but does not emit or absorb light. The continued expansion of the universe, now driven by dark energy, another enigmatic force, accelerates as time progresses. Support for the Big Bang Theory comes from multiple lines of evidence. The observation that galaxies are moving away from us, with more distant galaxies receding faster, aligns with an expanding universe. This phenomenon, first noted by Edwin Hubble, is described by Hubble's law and provides a cornerstone for the Big Bang model. Additionally, the predicted abundance of light elements, like hydrogen and helium, aligns closely with their observed levels in the universe, supporting the theory's nucleosynthesis calculations. The Big Bang Theory, through its comprehensive and testable framework, not only explains the observable data, but also provides a basis for exploring cosmic evolution. It continues to be refined and expanded by ongoing astronomical observations and theoretical advancements, allowing us to piece together the awe-inspiring chronology of the universe, from its fiery beginnings to its current state and beyond. The Big Bang Theory is supported by a multitude of observational evidence that collectively builds a robust case for this model of the universe's origins and evolution. These key pieces of evidence include the cosmic microwave background radiation, the expansion of the universe, the abundance of light elements, and the large-scale structure of the cosmos. One of the most compelling pieces of evidence is the cosmic microwave background, CMB, radiation, discovered by Arno Penzias and Robert Wilson in 1965. This faint glow pervades the entire universe and is considered the afterglow of the Big Bang. The CMB provides a snapshot of the universe approximately 380,000 years after the Big Bang, a time when the universe had cooled sufficiently for photons to travel freely for the first time. Measurements of the CMB, particularly those by the COBE, WMAP, and Planck satellites, reveal a nearly uniform temperature with slight variations. These tiny fluctuations correspond to the seeds of all current cosmic structure, indicating the initial conditions that led to the formation of galaxies and larger cosmic structures. The observable expansion of the universe is another cornerstone of the Big Bang Theory. In the 1920s, Edwin Hubble observed that galaxies are moving away from us, with more distant galaxies receding at faster rates. This phenomenon, known as Hubble's law, is consistent with an expanding universe and suggests that all galaxies were once closer together in the distant past. The relationship between the distance of galaxies and their redshift, a shift toward the red end of the spectrum due to their motion away from us, provides direct evidence of this expansion, which aligns with predictions of the Big Bang model. The relative abundance of light elements, specifically hydrogen, helium, and trace amounts of lithium, also supports the Big Bang Theory. During the first few minutes after the Big Bang, conditions were hot and dense enough for nuclear fusion to occur, forming these light elements in a process known as Big Bang nucleosynthesis. The predicted ratios of these elements, about 75% hydrogen and 25% helium by mass, match remarkably well with their observed abundances in the oldest known stars and gas clouds, further validating the theory. Additionally, the large-scale structure of the universe, revealed through observations of galaxy clusters and the cosmic web, supports the Big Bang Theory. Galaxies are not randomly distributed, but instead form a complex network of filaments and voids, patterns that match the fluctuations seen in the CMB. These structures likely arose from the gravitational collapse of initial density fluctuations present in the early universe, as predicted by the Big Bang model. Together, these lines of evidence create a consistent and compelling picture of a universe that has been expanding and evolving over the past 13.8 billion years. While the Big Bang Theory continues to be refined and explored through new observations and theoretical advancements, the core evidence firmly establishes it as a leading explanation for the origin and development of our cosmos. The acceptance of the Big Bang Theory by the scientific community was a gradual process that evolved through a combination of theoretical insights, observational evidence, and advancements in technology over the course of the 20th century. This journey was marked by several key milestones and contributions from numerous scientists. The story begins in the early 20th century with Albert Einstein's theory of general relativity, which fundamentally changed our understanding of gravity and the dynamics of space and time. In 1917, Einstein applied his equations to the universe as a whole but added a cosmological constant to maintain a static universe, as it was a prevailing belief at the time. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that galaxies are moving away from us, indicating that the universe is expanding. This observation was pivotal because it suggested that the universe had a beginning, contradicting the notion of a static, eternal universe. Simultaneously, Russian physicist Alexander Friedmann and Belgian priest and astronomer Georges Lemaitre independently proposed models of an expanding universe, deriving solutions to Einstein's equations that did not require a static cosmos. Lemaitre, in particular, introduced the idea of a prime Val atom, an initial highly concentrated state from which the universe expanded. But teams with temporary pairs of particles and antiparticles that pop in and out of existence, fleetingly borrowing energy from their surroundings before annihilating each other and returning that energy. These ephemeral fluctuations have significant implication for the fabric of the cosmos. In the early universe, during the incredibly brief yet consequential period of cosmic inflation, these minuscule quantum jitters were amplified to macroscopic scales as space itself expanded exponentially. Quantum fluctuations stretched out, seeding tiny variations in density that would later grow into the vast cosmic structures we observe today. It's these initially microscopic differences that eventually led to the large-scale distribution of matter in the universe, forming galaxies, clusters, and voids. The fingerprints of quantum fluctuations are imprinted on the cosmic microwave background radiation. Those slight temperature fluctuations we observe in the CMB are essentially the magnified echoes of quantum jitters from the dawn of time. In this way, quantum mechanics not only dictates the behavior of particles at the smallest scales, but also shapes the very large-scale structure of the universe. By studying these fluctuations, scientists continue to unravel the complex interplay between quantum forces and cosmic evolution, gaining deeper insight into the fundamental workings of reality itself. Quantum fluctuations, those tiny, ephemeral jitterings in the fabric of space-time, have a remarkable ability to catalyze the creation of particles through a variety of fascinating mechanisms. At their core, quantum fluctuations arise from the Heisenberg uncertainty principle, a fundamental concept of quantum mechanics, which states that certain pairs of physical properties, such as position and momentum, cannot both be precisely measured simultaneously. This principle implies that what we consider vacuum is not a void, but rather a frothing expanse of potential, teeming with transient bursts of energy. One significant process by which quantum fluctuations can lead to particle creation is known as pair production. In pair production, energy borrowed from the quantum vacuum materializes as a particle-and-a-particle pair. These pairs usually annihilate each other almost instantaneously, returning the borrowed energy. However, in the presence of a strong electromagnetic field, such as around a black hole's event horizon or within powerful particle accelerators, these pairs can be separated before they annihilate. If the particle-and-a-particle pair gains enough energy from their surroundings, they can become real, lasting particles, contributing to the observable matter in the universe. Moreover, during the rapid expansion of the early universe, known as cosmic inflation, quantum fluctuations were stretched to macroscopic scales. This stretching caused tiny perturbations in the density of the energy field permeating the universe. As inflation ended and the universe began to cool, these perturbations led to regions of slightly higher or lower energy density. In areas with higher energy density, conditions became ripe for converting that energy into particles. This process, known as reheating, essentially meant that the energy contained in those quantum fluctuations was transformed into a hot, dense brew of particles, a genesis event that seeded the universe with the matter and radiation we observe today. Thus, through these mechanisms, quantum fluctuations do far more than just fleetingly borrow energy. They lay the foundation for particle creation, contributing to the birth and evolution of the cosmos itself, echoing the profound interconnectedness of the quantum realm and the grand tapestry of the universe. Vacuum energy is a concept that seems almost paradoxical at first glance. It is the energy that is present even in the most seemingly empty stretches of space, devoid of matter or radiation. In classical physics, a vacuum will be characterized as an absolute void, a true nothingness. However, quantum mechanics reveals that even this void teems with activity due to the incessant dance of virtual particles. This ceaselessly fluctuating sea of virtual particles and fields contributes to a baseline level of energy known as vacuum energy. The existence of vacuum energy is fundamentally tied to the Heisenberg uncertainty principle, which implies that energy levels within any given point in space are never truly zero. This has profound implications for our understanding of the universe. One of the more compelling manifestations of vacuum energy is the Casimir effect. When two uncharged parallel metal plates are placed extremely close to each other in a vacuum, they experience an attractive force not attributable to any conventional electromagnetic force, but rather to the reduction in virtual particles between the plates compared to those outside. This effect offers a tangible glimpse into the subtle influence of vacuum energy. Vacuum energy is also a key player in contemporary cosmology, particularly in relation to the mysterious phenomenon known as dark energy. Observations of distant supernovae in the cosmic microwave background radiation suggest that the universe's expansion is accelerating, a phenomenon that could be driven by a form of vacuum energy. This dark energy, which constitutes about 70% of the total energy in the universe, is thought to be some manifestation of vacuum energy that generates a repulsive force, counteracting gravitational attraction and driving galaxies apart at an accelerating rate. In summary, vacuum energy is the undercurrent of the quantum world, a baseline hum of activity that persists throughout the universe. It challenges our classical notions of emptiness and reveals an intricate layer of the cosmos at both quantum and cosmological scales. Whether in the manifestation of the Casimir effect or the universe's accelerating expansion, vacuum energy serves as a testament to profound and often counterintuitive nature of reality, as dictated by quantum mechanics. The concept of vacuum energy is intrinsically linked to our understanding of the universe's origin and its subsequent evolution. In the earliest moments following the Big Bang, especially during the period known as cosmic inflation, vacuum energy played a pivotal role in shaping the cosmos as we observe it today. Immediately after the Big Bang, the universe was in an extremely hot, dense state, where the laws of classical physics break down, necessitating a quantum mechanical description. During this time, a scalar field, often called the inflaton field, dominated the dynamics of the universe. The energy associated with this field can be considered a form of vacuum energy because it was not tied to any particles or radiation, but rather to the underlying fabric of space-time itself. This inflaton field generated a repulsive force that drove an exponential expansion of space, known as cosmic inflation, which smoothed out any irregularities and homogenized the observable universe. As the universe expanded, quantum fluctuations in this vacuum energy field were stretched to macroscopic scales, seeding tiny density variations. These fluctuations are the genesis points that, over billions of years, evolved into the large-scale structure of the universe, including galaxies, clusters, and the cosmic web. This mechanism illustrates how quantum phenomena at the tiniest scales have profound implications for the structure and evolution of the cosmos. Furthermore, as cosmic inflation drew to a close, the vacuum energy of the inflaton field decayed, converting its energy into a hot, dense plasma of particles in an event known as reheating. This phase transition marks the transition from the inflationary period to the hot Big Bang, effectively setting the stage for the universe we inhabit today. The energy released during this process fueled the subsequent formation of matter and radiation, laying down the blueprint for the universe's ongoing expansion. In summary, vacuum energy is not just an abstract concept, but a fundamental player in the grand cosmic narrative. It induced a rapid early expansion of space, imprinted the initial conditions for cosmic structure, and facilitated the transition from a quantum-dominated early universe to the classical universe filled with matter and radiation. Through these roles, vacuum energy underscores the profound connections between the quantum realm and the vast expanse of the cosmos, each influencing the other in ways that continue to intrigue and challenge our understanding. The universe undergoes endless cycles of expansion and contraction. In this scenario, the Big Bang is not an isolated event but part of a recurring cycle, driven by the physics of cosmic brains and string theory. Prominent variants of this model include the ekpyrotic universe, where collisions between brands in higher dimensional space trigger repeated cycles of cosmic birth and death. While more speculative than the Big Bang model, cyclic models aim to address puzzles such as the universe's initial conditions and the nature of dark energy. The steady-state theory, once a popular alternative to the Big Bang, proposes that the universe has no beginning or end but remains in a constant state, with new matter continuously created to maintain a constant density as it expands. Although this model accounted for the observed expansion, it fell out of favor primarily due to its inability to explain the CMB and the accumulation of observational evidence supporting the Big Bang. Quantum mechanics also contributes to cosmological modeling with ideas like the quantum creation of the universe. This model suggests that the universe could have spontaneously originated from a quantum vacuum fluctuation driven by the principles of quantum mechanics. Stephen Hawking and James Hartle propose a no-boundary condition where time behaves like another dimension of space at the universe's inception, smoothing out the singularity and enabling a quantum birth from nothing. Finally, there are more exotic theories, such as the multiverse hypothesis, which proposes that our universe is just one of potentially infinite parallel universes within a larger multiverse. Each universe could have different physical constants and laws. This hypothesis often arises from interpretations of inflationary theory and string theory, suggesting that different regions of space could inflate at varying rates, leading to distinct, causally disconnected universes. In summary, while the Big Bang theory, bolstered by cosmic inflation, remains a dominant model explaining the origin and development of the universe, other models like the cyclic universe, steady-state, quantum creation, and multiverse hypothesis offer compelling alternatives or extensions. These cosmological models reflect humanity's ongoing endeavor to decode the mysteries of the cosmos, each contributing unique insights and posing new questions about the nature of existence and the ultimate origins of our universe. The steady-state theory and the Big Bang theory offer fundamentally different perspectives on the origin, structure, and evolution of the universe. These two models diverge in their assumptions about whether the universe had a beginning and how it has changed over time. The Big Bang theory posits that the universe began approximately 13.8 billion years ago from an extremely hot and dense state, often referred to as singularity. According to this theory, the universe has been expanding ever since, cooling and evolving to form the galaxies, stars, and planets we observe today. Key pieces of supporting evidence for the Big Bang theory include the cosmic microwave background, CMB, radiation, which is the afterglow of the early universe, and the observed redshift of distant galaxies, indicating that the universe is still expanding. Additionally, the Big Bang model accurately predicts the relative abundances of light elements, such as hydrogen and helium, produced during the first few minutes after the initial explosion, a process known as Big Bang nucleosynthesis. In contrast, the steady-state theory posits a universe that has neither a beginning nor an end, maintaining a constant average density over time despite its continual expansion. Proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi in 1948, this theory suggests that new matter is continuously created to fill the void left by the expanding universe, allowing it to remain in a steady state. In this model, the universe is eternal and unchanging on large scales, meaning it always looks the same at any point in time and space. This continuous creation of matter happens at such a slow rate, about 1 hydrogen atom per cubic meter per billion years, that it evades direct detection. One of the primary differences between the two theories is their predictions about the background radiation of the universe. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory and posed a significant challenge for the steady-state theory. The uniform and isotropic nature of the CMB fits well with the Big Bang model, which predicts that this radiation is a relic heat left over from the early universe when it was much hotter and denser. Moreover, observations of distant galaxies and quasars support the notion of an evolving universe. The Big Bang theory accommodates these observations by suggesting that the universe looked different in the past, showing younger galaxies and a more active state of star formation. In contrast, the steady-state theory would require the properties of galaxies and other cosmic structures to remain constant over time, which is inconsistent with the accumulating observational data showing an evolving universe. While the steady-state theory presents an elegant and unchanging view of the cosmos with continuous matter creation, it struggles to account for key observations such as the cosmic microwave background radiation and the evolving nature of galaxies. The Big Bang theory, with its framework of a universe that began from a hot, dense state and has been expanding and cooling ever since, offers a more comprehensive and supported explanation for the multitude of phenomena we observe in the cosmos. The cyclic model of the universe is a fascinating and speculative alternative to conventional Big Bang theory. Unlike the standard model, which posits a singular beginning with a subsequent expansion, the cyclic model envisions a cosmos undergoing endless cycles of birth, evolution, and rebirth. These cycles could each last over vast time scales, hundreds of billions or even trillions of years, resulting in a universe that periodically renews itself. One of the most well-known cyclic models is the ekpyrotic universe, which draws from ideas in string theory and higher dimensional cosmology. In this model, our visible universe is a three-dimensional membrane, or brane, situated in a higher dimensional space. This brane periodically collides with a parallel brane, releasing enormous amounts of energy that effectively initiate a new cycle of expansion and contraction. Each collision produces a Big Bang-like event, setting the stage for the creation of matter and radiation, similar to the start of a new cycle. The term ekpyrotic is derived from the Greek word for conflagration, symbolizing a fiery rebirth from destruction. The cyclic model offers potential explanations for several perplexing cosmological issues. For instance, during each contraction phase, any irregularities and anisotropies in the universe's structure could be smoothed out by a mechanism similar to inflation in the traditional Big Bang model. This would ensure a homogeneous and isotropic starting point for each new cycle. Moreover, the cyclic framework could potentially provide an elegant explanation for the smallness of the cosmological constant, a parameter that describes the energy density of the vacuum and drive the universe's current accelerated expansion. In the cyclic context, this constant might be dynamically adjusted over each cycle, alleviating the fine-tuning problems that plague other models. However, the cyclic model also introduces new challenges and unanswered questions. A critical concern is how each cycle transitions from contraction to expansion without resulting in a singularity, a point of infinite density where conventional physics breaks down. Theoretical physicists work on resolving these issues by employing advanced mathematical frameworks and extending ideas from quantum gravity and string theory. Additionally, observational evidence presents hurdles. The cosmic microwave background, CMB, radiation's highly uniform nature, and the large-scale structure of the universe have traditionally been interpreted within the context of a single expanding universe. While the cyclic model needs to replicate these observation successes, it must also make unique predictions that can be tested through astrophysical measurements. In summary, the cyclic model posits a universe in a state of perpetual renewal, cycling through phases of birth, expansion, contraction, and rebirth. This perspective provides innovative solutions to cosmological puzzles like the horizon problem and the cosmological constant, but it also introduces complex challenges that remain subject of active research. Embracing this model requires reconciling it with existing observations while continuing the quest for a deeper understanding of the universe's fundamental workings. As theoretical physics advances and observational techniques improve, the cyclic model may either find its evidence or yield to more comprehensive theories regarding the cosmos's nature. In the grand tapestry of our universe, dark matter and dark energy weave threads that remain largely mysterious, yet are crucial to the fabric's integrity. Scientists estimate that only about 5% of the universe is composed of familiar visible matter that forms stars, planets, and galaxies. The remaining 95% is split between dark matter and dark energy, with dark matter constituting roughly 27% and dark energy a staggering 68%. Dark matter, though invisible and elusive, behaves like cosmic scaffolding, holding galaxies together with its gravitational pull. Without it, galaxies would not have the structural integrity to withstand their own rotational speeds. Yet, despite its critical role, dark matter does not interact with electromagnetic forces. It neither emits nor absorbs light, making it detectable only through its gravitational effects. On the other hand, dark energy is even more enigmatic. It's the unseen force driving the universe's accelerated expansion, a discovery that upended prior cosmological models. While dark matter binds the universe, dark energy pushes it apart, both forces integral to the complex dance of cosmic evolution. The universe's beginning, often referred to as the Big Bang, presents a mind-boggling scenario where the laws of physics, as we know them, were both incredibly relevant and uniquely challenged. Approximately 13.8 billion years ago, the universe was compressed into a singularity, a point of infinite density and temperature. During this infinitesimally brief moment, known as the Planck epoch, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. However, the conditions were so extreme that our current understanding of physics, including general relativity and quantum mechanics, becomes incomplete and potentially divergent. As the universe began to expand and cool, it transitioned through various epochs where the laws of physics gradually took their forms. Within the first fraction of a second, the fundamental forces differentiated from one another. The quark-gluon plasma, a state of matter where quarks and gluons roam freely, eventually condensed to form protons and neutrons. As the universe continued to cool, over the course of thousands of years, atoms began to form, leading to the creation of the first simple elements like hydrogen and helium. It was during these early moments that the universe's fundamental properties were set, governed by the same physics laws that dictate the motion of galaxies, the life cycle of stars, and even the behavior of particles in a laboratory today. These astonishing transitions illustrate how the laws of physics not only apply but actually emerge and evolve from the universe's nascent chaos. General relativity, formulated by Albert Einstein in 1915, fundamentally reshaped our comprehension of gravity and the fabric of space-time, offering profound insights into the universe's origin. Unlike the earlier Newtonian conception of gravity as a mere force between masses, general relativity describes gravity as a curvature of space-time caused by mass and energy. This paradigm shift enables us to understand the dynamics of cosmic structures on a grand scale, revealing how massive objects like stars, planets, and even light navigate the contours of this curved space-time. In the context of the universe's origin, general relativity provides a mathematical framework for the Big Bang theory. According to Einstein's equations, the cosmic history of the universe can be traced back to a singular, incredibly dense, and hot point, the singularity. This singularity marks the starting point of space-time itself, around 13.8 billion years ago. Solutions to these equations, such as a famous Friedmann-Lemaitre-Robertson-Walker metric, describe how the universe expands over time. Importantly, general relativity also predicts phenomena such as a cosmic microwave background radiation, a remnant heat from the Big Bang, which has been observed and measured, offering compelling evidence for this model. Thus, general relativity not only aids in conceptualizing the universe's beginnings, but continues to be an indispensable tool in exploring the vast cosmic expanse and its evolution.